Okay, so as part of this lecture, what we wanted to do was spend some time on understanding what the CPU is. And by understanding the CPU, we don't mean that we'll dive into the actual hardware implementation. It's just that, the functional idea of a CPU that you should have with you to be able to reason on top of. And again, we started our journey with 1970s, how the systems were back then. And, Mohammed mentioned that there was a CPU which was linked to the memory, and it would essentially fetch the instruction and the data from the memory. And in some sense, we then said that the zeros and ones that were resident in the memory, well, they were on a punch card. So meaning that the punch card was essentially the memory, and so anywhere that there was a zero, a hole, would convey, let's say, a zero, and anywhere, uh, let's say, there was no hole, that conveyed like a one. So now what we should spend our time on is what the CPU did, how you can imagine it to be. And in today's time, you will find all such information in something called the programmer's model of the CPU. So if you were to look at any modern day CPU, just look for the programmer's model and you'll get the imagination or the picture that you should have for the current CPU. Okay, so a CPU then, for all practical purposes, we can think of it as a glorified calculator, which has the ALU, the arithmetic and logical unit, and then it takes in two operands, we say, and where those operands come from, we'll talk about. And then it computes the calculation, like computes whatever the operation on these two operands, and it gives out an answer. Right? So, and then the question is that the ALU is capable of performing, let's say, addition, subtraction, multiplication, and the division operation. And it is guided by the control unit. So there is also somewhere control unit, which essentially figures out as to what calculation the ALU is to perform. And then talking about these operands, the question is, okay, where do these operands come from? The answer is, well, they come from memory. And this answer also goes to the memory. But where to fetch the operand from, where to send the result to, well, that is dictated by the instruction. So somewhere in the memory then is a bit pattern, and that bit pattern we mentioned was on a punch card, right? So each line on this punch card, then you can think of it as either instruction or it was data. Right? And whether it is a data or an instruction, well, the details of that depends on how the CPU is implemented, how it is interpreting those bits. But essentially, there would be something called program counter inside a CPU. This is true even today. And the program counter is essentially keeping a track of which address in the memory, which location in the memory to fetch the bits from. And those bits, and that's my claim, those bits are going to be treated like an instruction, right? Instruction for the CPU. So these bits then would be fetched over the buses. Buses are essentially wires. So the CPU is connected to the memory through wires, and so over the wires it is understanding that, okay, these are the bits, and these bits are then essentially treated like instructions. And as you can imagine, this instruction then or the bits that correspond to the instruction is what the control unit is using to figure out as to what operation the ALU should perform. All right. Not only that, but some instructions will also tell our CPU as to, hey, where to get the first operand from, where to get the second operand from, and where to write the answer to. Right. So this is how you can imagine a CPU to be, or a system to be rather. Yeah. Go
Can
ahead.
you add some example, like let's say if the instruction was add, then the bit
How?
pattern could be 101 something. So
Fair. Yeah, that's a good one. So how about this? Let me draw a clean picture and then I'll walk through an example. And then we'll actually improve on that example to connect it to the physical world of 1970s. Okay, so here we have our CPU. We talked about the fact that it has the ALU, which gets its operand from somewhere, and then it also generates an answer. And here then we, let's say, had a bus, and bus is essentially multiple wires denoted by a line and a slash on top of it. Right? A single, line is a wire, and a slash on top of it essentially means multiple wires. So each of these are multiple wires. So somewhere there was control unit, again connected like so. There was something called instruction buffer, and that fed into the control unit for it to understand what the instruction is. And then we also said that there was like a program counter which kept a track of which location in the memory to fetch the bits from. And how many bits to fetch? Well, that is also predetermined based on the architecture of the CPU. So in this case, let's say it was 8 bits, for example, right? So it would fetch 8 bits and the 8 bits would convey the operation. Okay, and where would it fetch these? How would it fetch these? So, well, there would be like a, we call it address bus and data bus. And the same data bus also served as an instruction bus. So if the program counter value was put here, it would go, let's say program counter was hex 2, so it would go ahead and fetch the second byte and it would come from here to here. Okay, now we'll kind of paint a real picture also as to how the memory evolved with time and how CPUs evolved with time. But now going back to Mohammed's nudge, which is, let's say the ALU was to perform add operation on memory location, for example 10 and 11, and put the answer on the memory location 12. Now the reads and write in the current case, in the narration that I'm doing, are happening to the same memory. Right? When we paint a picture of how things were in 1970s, a physical picture, the writes would change a little bit, and I'll speak to it more in a bit. But okay, so let's say the number 1 was put on 10th location and number 2 was put on the 11th location, and add instruction was available on the second location which the program counter was pointing to. So what it would mean is that there would be some encoding, some 8-bit encoding, let's say 101, and then there was some notion of, or rather let's say there was 1 representing the add operation, and there were how many, 6 more bits left?
Yeah, 6.
Actually,
we can reserve 3 for the offset or something like that. We are designing our own essential opcode.
Correct. So what I want to do is somehow, let's say let's make it 16. So let's say the instruction is 16 bits, and the reason I'm wanting it to be 16 bits is because, well, 10, 11 and 12, the 3 information cannot be represented. Okay, so let's say we have 16 bits, 1 instruction for 16 bits. So what we can do then is reserve 12 bits for the memory addressing, and then the remainder 4 bits for opcode, operation code. So the 4 bits here can go from all zeros to all ones, and then you can associate an operation with each of these 16 values. So let's say for whatever reason 1011 was for addition. Right? So then 1011 being here will convey to the control unit that, hey, I am supposed to select the add operation. Right, and then the later set of 3-4-bit set. So the first, let's say, conveys the address from where it should pick the first operand. So this then would then become 1010 for 10, and then the second set, or rather this set of 4 bits would convey the second operand, so that was 11, so that would then become 1011, and then the answer needs to be written back to the 12th, so that would be something like so. So then when we are talking about add content of 11 and 12, 10th and 11th memory location, and put the summation in the 12th memory location, so the bit pattern which is right here will convey the operation code, the op code, that is what we call, followed by the first operand, the second operand, and the third operand. So essentially the value at memory location 10 will appear here, value at memory location 11 will appear here, and the answer that is generated will be sent back to the memory location 12. Right. And so all of that information typically is encoded in the instruction itself. Now again, this is a dummy instruction that we have created on the fly. Things are a little more involved and complex. In this case, you'll notice that the memory is also limited to 16 locations, right? Just because we have 16 bits to address each of the location, right?
4 bits.
4 bits, sorry, yes, 16 values, 4 bits,
4 bits.
to address the locations in the memory. But long story short, this is a good imagination that you can have. Now, I had initially mentioned that I was talking about the writes to the location 12, and back in 1970s, things were a little different. And so how did things go? So you had the CPU, which was essentially connected to a punch card system, right? So there was punch card system. So the inputs would come from, well, punch cards, or you can say the instructions would come from punch cards. And we can now talk about the values, the input values coming from switches. Right? And the outputs would then go to bulbs. So punch cards cannot be written to because you have to poke a hole in them, and once a hole is kind of drilled or poked into it, that is easy. But what is not easy is to cover up a hole. So you can set like a 1 to 0, but you cannot set a 0 to 1. So writing back to a punch card made no sense. So you instead just had the instructions here, and whatever input values were required for your computation. Let's say you want to compute the circumference of a circle, so you can then give the value of pi as certain combination of switches being on and off, and the value of r can also be given as certain other value of switches as on and off, and then whatever the answer is, that would be flashed as bulbs glowing up, right? That is how it usually was. And you can imagine the switches here to be an array of switches, and each array correspond to like one variable or one data packet. So this is how the CPU, memory, and the instructions back in time were.
So Piyush,
Right? But this, yeah.
Sorry, I just want to for my understanding and maybe for some of the viewers, the instructions, if we were to retrofit whatever model you had just described earlier, like 2 slides back, and retrofit that into 1970s model. So here the instruction would basically work almost similarly. Instead of reading it from a memory, we would read from the punch card.
Yes.
And here the operands would also be some location, but it would not say, hey, go and read the location in the punch card. It might say, hey, go and read the row number blah blah from this
switch matrix.
Switch matrix.
Yeah.
So that could be the offset to that.
That
and
is correct.
The answer would be like, hey, go and update the row number this to the bulb matrix.
Yes, yeah, that is also true.
Everything would like completely remain same.
Right. And this is where, if people are watching, let's say, any old documentaries on computers, or the imitation game movie,
Enigma.
Yes, the Enigma, you have a lot of regulators and a lot of switches. Well, this is what it was doing. It was setting the initial conditions for your computation. Now things evolved a little bit, right? So for example, the CPUs originally would do this, take their constant parameters from somewhere and instructions from somewhere. But later turns out you can make your constant parameter, part of your punch card. So then you can slowly eliminate this and only have, input coming from punch card, output going to the bulb. Input meaning the data input. Okay, so this was one. Now, what they did, and I think when Bill Gates and Paul Allen, started the Microsoft company, um, was it Altair 8080 or something like that? What it would do is, and this is again, how punch cards evolved. So punch cards evolved into a tape, and and you can imagine. So punch card was like limited, and let's say you were to encode these number of bits. So if you poke a hole here, that's a 0. If you skip it, then that's a 1. If you poke a hole here, that's a 0, and hole. So this is how you would encode things, right? And you would, but the size is limited. So now what they did was they said, hey, we would have a tape. Let's have a tape, and then a row on the tape could have like hole or no hole, hole, and so this is conveying some bit pattern now. And so you would have many of these. And now what they did was they had like a rotatory reader. So this would kind of roll over, and this rotatory you can say this rotatory reader, and it's going to rotate this way. So it's something of this, and it had switches here. So what would happen is as the tape rolls over, you are essentially pressing different switches if there is no hole in that position. And if there is a hole, well, then the switch doesn't press, it stays unpressed or open. And now based on these switch presses, the computer is figuring out inputs coming to it.
It's basically like a keyboard.
It's basically like a keyboard, and
printed by the tape rather than a human.
Exactly. And now what you can imagine is, so there was this switch matrix which was inputting, which was used for the input constants and all of that. They ended up replacing the punch cards with kind of a dynamic, time. Would you say time multiplexed or sampled in time?
Yeah, I think quantized.
Quantized, yeah. Every 1 minute or 1 second, you would come and look at the switch matrix, and just before you do that, you would rotate the.
So you basically sync it once, like the time you sample the switch matrix versus the speed of your rotary wheel, and that's it.
Right, and so all of a sudden now you have a way to feed your program a little faster. Earlier, you needed people to load the program manually. Like they would need to kind of poke holes and then load the punch card onto the system. But now all of a sudden the research scientists who needed to do computation, they could just come and hand you a role, and that role is the program. And then you can then also imagine that instead of bulbs now, you could also go for a machine that poked holes on a tape. So you are handed a tape as a program, and later you hand back a tape with holes and not holes in it to the researcher and be like, hey, read these values and figure out whatever they are. Okay, that is how things evolved, and then we could talk more about it. That later what happened was slowly people figured out that the electrical coils can save magnetic energy in them, store magnetic energy. So the absence and presence of magnetic energy can be a 0 or a 1. Things evolved from them. But long story short, the fact that there was an instruction encoding, that stayed. The fact that the CPU has control unit, ALU, program counter, that stayed. And things have only gotten better in terms of implementation. Now, before we end this lecture, I want to call out or bring attention of people to this one point, which is the encoding of the instruction is called the instruction set architecture, and this is very important. And the importance is this: so you have the actual hardware that is going to do the computation, and that can evolve with time. And then there is a software. In our case, we talked about that being on punch card or on so let's say if you sorry, punch card or tape.
Yeah.
And let's say over time the hardware became better, meaning we went from punch card to rotary encoding. Would you need to write your software again? Well, in case of punch card to tapes, maybe yes. But let's say the tapes are still around, and now the computation can be done much faster. So new hardware has come in. The problem is you now again have to create another tape with the same program. So what people did is they sealed onto this idea of ISA that serves the interface between the hardware and the software. What does it mean? It's like as long as the instruction encoding is the same, if the underlying hardware changes, but it respects that ISA, respects that instruction encoding, then your same software can be run on that newer hardware. And that's an idea that is still true today. The Intel, you can upgrade a processor on your Intel, let's say, machines, go from like i7 to i5 to i7, and you don't have to rewrite your programs, you don't have to recompile them. And the reason to that is i5 and i7 support the same ISA, and the software is also kind of having its instruction in the same instruction encoding. ISA is called instruction set architecture. It dictates the encoding scheme of an instruction, and as long as that is constant, the underlying hardware can change and the software need not. And also the software writers can write their software independent of the details of the hardware. They need not know what the ALU is, what the control unit is. So that way life is simple, and progress is faster. So ISA, one of the takeaways from this lecture should be the ISA, and again some imagination around how things evolved.
In fact, I would say this picture right here is kind of true even today, like almost to the dot, right? Just some memory, there might be some changes in the way memory operates, but I think the underlying idea of how an instruction, or rather how a set of bits are interpreted as instructions, as operands, as opcodes,
that remains the same. All right. So, and well, I did not talk about it here, but we'll cover it later, which is, so this again is coming from the 1970s, where the CPU would only execute one program. Right. Later, what happened was CPU evolved to execute multiple programs, and that then leads to the concept of operating system. But the CPU also had this ability, and after 1970s, over time they evolved to handle something called interrupts, and we'll talk about that in kind of the subsequent lectures. But again, there are few additions that happen to the CPU, and they evolve. And as you come to the 2000s and 2020s, things have changed so drastically. But again, the underlying concepts are same. Go ahead, Mohammed. Do you want to add anything to this?
Nothing to this. I think this is a nice end to this concept.
Okay, perfect. So with this, then we'll see you in the next one.